Muitas coisas. Sim, sim, tenho que...
Stefano Camera from Università He has been spending in Italy in Brazil. And exciting times are approaching for cosmology, for merging a lot of different observations. So, Stefano, tell us about it.
Okay, thanks. Thanks for this opportunity to talk here, and thanks again for the invitation and the very warm welcome that I've received this week. It's been great. Apart from the weather, that now this week is great, but last week wasn't that much. But apart from that, I'm really, really happy of having been here in Sao Paulo. Today what I'm going to talk about is basically my main research topics that all kind of revolve around this idea of doing synergic cosmology across the spectrum with different observables and different at different wavelengths. And well, the basic idea, of course, is what that you want to understand something about the universe. What people have done for like millennia when trying to study where we are was just looking at stars, but now we know that stars are just a few per mil of the total content of the universe, on top of which we have the matter we know, the matter that's part of the periodic table of elements, etc., which again is only like 5%. The rest being a huge bunch of what we call cold dark matter in a huge empty dark of cosmological constant that amounts for something like 70% of the total quantity of energy of the universe. To be more quantitative, the problem, well, the main problems that we have to face in cosmology nowadays about our concordance cosmological model is that the matter of the universe appears to be, for the most part, in some exotic form, some exotic origin, what we call dark matter. And then in particular, that there are two stages of the evolution of the universe, of the history of the universe, that are extremely distant in any possible way, distant in time, distant in scale, distant in energy, but yet they are remarkably similar. And these two stages are, of course, the stage, what we think happened really, really after the beginning of the universe, what we call inflation. Inflation, more than a theory, is a paradigm in the sense that gives us the means by which we can explain what happened later, but we don't really have yet a single theory that explains everything. And this is a problem because we need to trim down this huge theoretical landscape, right, if we want to understand something more. And the means by which people have tried to do that in the past, and even now, is by looking at imprints of inflation, and in particular, by searching for B modes, so gravitational waves coming from this inflationary epoch, or by looking for primordial non-Gaussianity. So the possibility for signatures of the possibility that primordial fluctuations in the very early universe were not distributed Gaussianly, or at least not completely in a Gaussian way. The phase, which is very similar in the sense that it is another phase of accelerated expansion, is what we call the dark energy or cosmological constant dominated phase that is happening really nowadays. And the questions there are, of course, whether this is just a seemingly fine-tuned cosmological constant, lambda, or if, like some of the recent claims seem to support, if this is yet another mysterious scalar field, some dark energy. And, well, the most important, well, for me at least, one of the questions that is really interesting is whether these things that we happen to don't know about the universe, be them either cosmological constant, dark energy, even dark matter, whether they are just a failure of our understanding of how gravity works on the extremely large scales of the cosmos. So these are all the main questions that we are all interested in, since we are here, I think. But this was just to put things into context. And the way by which I try to address these questions is by looking at synergies. And for the rest of the talk, this is one slider about what I mean by synergies, right? There's many ways, but you can do like any synergetic and synergistic approach to study the large-scale structure and to study the universe. I'll be talking about mostly of correlators. So we take different cosmological perturbations and we try to mix them with each other. And by cosmological perturbation, I focus again mainly on scalar fields. So suppose you have a scalar function, which could be temperature fluctuations in the cosmic microground, could be like some density perturbations. This is a function of time and space. Time evolution is deterministic, so we know how things evolve in time. but the spatial properties of this field is stochastic. And this probably, at least what we tell each other, is that this stochasticity comes from the inherent stochasticity due to the quantum properties, the quantum nature of perturbation and inflations. So we cannot predict whether a galaxy will be formed there or not, given the initial condition, which we don't know, but we can predict, of course, the statistical properties of these fluctuations. And these are mainly described, I mean, most of these fluctuations are described as a averaged, as a density contrast, let's say, so they average to 0, so looking at the mean is not really insightful. But what we can study is the second moment of the distribution, which is the variance. And if you take the variance in the sense of, well, actually the covariance, so if you take this perturbation at 2 points in space, what you can construct is a cosmological two-point correlation function, which for homogeneity and aisotropy only depends on the separation between the 2 points. In principle, even only on the distance between the 2 points, if we were able to observe objects where they really are, we cannot. So this breaks some of the other aisotropy. But at least homogeneity takes this to be only a function of the distance. You can do the same exercise in Fourier space. So you expand your observable in Fourier space, and what you end up with is the variance in Fourier space, which we call the power spectrum. They contain exactly the same amount of information, but they have pros and cons, and particularly one of the main pros of looking at the power spectrum is that, at least on linear scales, when perturbations are small, the power spectrum Fourier modes of the power spectrum evolve independently. And so you can, like, if you see error bars on a plot of the power spectrum, they are really error bars, right? They are not correlated. They don't talk to each other. Both of these approaches are, let's say, more theoretical in the sense that you assume that you can observe a big volume of the universe and do this exercise. Another way to do this in a more anthropocentric view, if you want, by thinking that what we are actually observing is perturbations on the sky. And, well, quantum mechanics, you have a perturbation on the sky. What you do, you take spherical harmonics, so you expand your perturbations on the sphere in spherical harmonics, and then the variance in the spherical harmonic coefficients, Lm, what we call the harmonic space, or, like, loosely speaking, the angular power spectrum. And the nice thing about the harmonic space approach is that allows you to correlate things not only at different positions, but also in, like, radially, angularly, but also radially, right? So you can compute the cross spectrum between redshift Z and redshift Z prime. Again, this is just what you do when you have, like, a spectrum of, or correlation of the observable. And when I talk about synergies, for the rest of the talk, I will mainly talking about, like, cross correlation between different observables. So instead of taking the auto spectrum of F with F, you take the cross spectrum with F with G. And in principle, the question that you may ask is that, well, the information about cosmology is contained, is encoded in the perturbation. So what's the point of doing this? Well, the main point what I want to convince you, if you're not convinced of that already, is that we cannot really, I mean, this is true if we were able just to observe the spectrum itself, that would be great, we don't need anything else, but we cannot really observe that because we have to face with measurements. And so we have observational systematics that we have to deal with. We have noise, of course, on the measurements, and we have what we call cosmic. So the fact that the largest cosmic scales can only be probed up to a certain accuracy, precision, sorry, because there's only one universe observed. And so there are, on very large scales, only few modes available to average over. So the error bars are very large. So what I want to convince you about that you can choose, if you're careful enough to choose the right observables to cross-correlate with each other, you can leverage on the power and get rid of some of these problems, even cosmic variance. And I will start with the last one. Yes. Oh, Dirac and Kronecker. I'm just being very, very, pedantic. And so, with what you can do synergies? Well, with everything, right? Because the nice thing about the large-scale structure of the universe is that everything is correlated. So we cannot observe, this is a nice snapshot from a simulation. We cannot observe, of course, the actual large-scale structure, but we observe things that are in the large-scale structure. And they all correlate with each other because they all sit in the same large-scale structure. So to some extent, they are all correlated. The means by which people have studied the universe, the late-time universe, in general, the universe, has been looking at mainly, well, of course, the CMB, but if you think of the large-scale structure, has been mainly by studying galaxy clustering, so the way galaxies clump together, right, tracing the large-scale structure, or by looking at with lensing. So the effects of the intervening matter between distant galaxies and us, which makes light rays being bent and scattered all over the place. And this is the weak lensing effect. But they will also go further and say that we can do even more. So you can look at all this with just not CMB, but also CMB secondaries, so with lensing and other things, and even at different, very distant wavelengths. And in particular, I'll show you something about using gamma rays, which don't look very cosmological in general, but you can actually also learn something by looking at correlation with gamma ray observations, or intensity mapping, which is very timely and a very new sort of observable. People are very excited about that. Yes? Intensity mapping. Yeah, with what? Well, mainly neutral hydrogen. Yeah. This is neutral hydrogen is the most advanced in this sense, but people have also started to look at carbon monoxide and carbon lines in general. Yeah. And this is a great time to do that. We were talking about that with Riccardo before. This is really the time when you can look at the large-scale structure. So this is a poster that I stole from the European Space Agency's website that shows the ESA fleet across the spectrum. And amongst these, well, there's something that is interesting for cosmology. Of course, Euclid, which I'll be talking about later, a bit of JWST, but not really Planck, of course, and in the future, LISA. But then if you put on top all the other experiments, well, not even all. This is just a selection, probably biased, even not willingly biased, a selection of surveys that you can look at and use to study the large-scale structure. There's plenty of them. That's really a lot. And these are all surveys that are either like finishing their final stages, or they actually really started. So there's plenty of information that you can use. And they really go through all the spectrum. So from the longest wavelength with the SKA observatory, and this week there's the science conference of the SKA in Görlitz in Germany is taking place. And then you have on the CMB, you have new instruments. You have Einstein telescope and LISA in the future to study gravitational waves from the large-scale structure. Euclid, again, that I mentioned already, something that people here is involved with, which is JPAS, and all the way Rosetta and X-rays and gamma rays. So there's really a lot of things that you can do. So just unleash your imagination, and you can probably do like great things with this. So that will be focusing on is this, and in particular, I'll be talking about the Euclid satellite as a paragon. Euclid's European Space Agency medium class mission. You can see here when it was in Turin at the Thales Alenia Space Laboratory, where it was partly constructed. And this is me. This was before COVID. The mask had nothing to do with that. But every time I see this image, this is with 2019, it always makes me wonder. And this is like, this was a thermal module, but like 70% of what you see in this image, apart from me, was sent in space later. And it was successfully launched 1st of July 2023. Now it's finishing the first data release internal, and we will have data available really soon that will be then analyzed by the collaboration, and in a year's time we'll hopefully release the main papers. Here you see a beautiful slide that shows the first 1% of the Euclid-wide survey observed in this area here. This is Gaia map. And well, the images are beautiful. If you just want to pop in the website, you can see fantastic stuff that is already available. The other thing that I'll be talking about is the SKA observatory. SKA will be the largest radio telescope on Earth, and also the largest scientific instrument ever built. It's the second, so it's managed by an intergovernmental organization for science, the second in the world after CERN. And it will be built in 2 locations. So in the Karoo region in South Africa and in Western Australia here, with 2 different instruments, and managed globally by the headquarters in Jodrell Bank near Manchester. What the countries that you see highlighted in blue are countries that are either member states or observers. Member states, as of June 2022, rather old, are marked by this asterisk. And then, given that there's a long-standing tradition of radio astronomy in Africa, part of what the SKA will also to do is like to engage with African partner countries that you see highlighted here. SKA, as I say, was the largest radio telescope on Earth, and these are the 2 locations. And it will cover the range between 50 megahertz up to 15 gigahertz, so a very large bandwidth. And in particular, in Australia, it will be composed by the antennas. And we have first light last month. These antennas are of order of like more than 100,000, covering a large total collecting area. And if you want to compare it to the best similar instrument in the world now, this is LOFA, the low frequency array in the Netherlands. And so SKA low, the low frequency instruments will have 25% better resolution, it will be 8 times more sensitive and more than 100 times faster in scanning the sky. And it will operate between 50 megahertz, so the very low frequency up to 350 megahertz. In Australia, on the other hand, we'll have about 200 big dishes that will cover the rest of the bandwidth between 350 megahertz up to 50 odd gigahertz. This is the mid instrument with a maximum baseline envisaged of order 150 kilometers and with the huge collecting areas, which for some reason they tried to match to some tennis courts. If you want to compare it again to the best similar instruments in the world as of now, which is JVLA, the Jansky Very Large Array, SKA mid will be 4 times, have better resolution, 5 times more sensitive, and 60 times the survey speed. So this is the state of the art. But once we wait for the actual surveys of the SKA to start, because the SKA is really being built at the moment, there are already things that you can do with what we are called precursors and pathfinders. A lot of instruments that are either located at future SKA sites, like the Australian SKA Pathfinder, which funnily enough is a precursor, or Meerkat, which is the South African one, or other pathfinders which are instruments engaged with SKA-related science and technology. And I myself, I have something to do with some of these. So this is the setup. And let's start then to see how we use all these synergies that we can build at different wavelengths with Euclid, SKA, and other things to beat in particular cosmic variance. So as I was saying, cosmic variance is the problem that we only have very few modes on large scales to probe effects that happen there. And the paragon that I use as an example is galaxy clustering. So galaxy clustering, you take a number density of galaxies in a given patch of the universe, and you can construct a number density, big delta, by comparing it to the mean, the average number density that you have. Now, linear theory tells you that this is directly related to the density of fluctuations in the universe, and this is like reasonable, right? And you have a bias on top. But the problem is that we are not observing galaxies where they really are. We observe galaxies, people would say, in redshift space. Literally, we observe galaxies on the past light cone, the surface of the past light cone. So you have to take into account that the positions that you infer from the redshift and the angles are not the real position in an unperturbed universe. And this induces a series of corrections, other terms that enter this galaxy clustering contrast, which are related to the velocities of the galaxies, that they're really high, they contribute to the redshift, to the lensing, so the angles that you measure are not the real angles at which the galaxies are located, because lensing affects this perpendicular direction, and also a bunch of what we call relativistic effects. Relativistic effects that are like Sachs-Wolf effect, like integrated Sachs-Wolf, like Shapiro time delay, all these sort of things that are actually really important because they will allow us, in principle, to probe general relativity, the validity of general relativity at linear level on cosmological scales, where it has never really been probed in the sense that we only have strong measurements of relativity on strong field regime, but yet they haven't been measured. And usually when people analyze this kind of data, they focus on density and redshift space distortion, which is a subset of this velocity term. And if you want to look also, if you go deep enough, you should start taking into account also lensing. But the other terms are usually neglected because they are really tiny. Among these tiny effects, there's one that is dominant with respect to the other. So this is the one that you are more likely to measure if you ever manage to. And this is a Doppler, is another velocity, is a Doppler term that enters there. Yeah, in fact, it should be there. The Doppler actually has two terms. One is volume related and one is velocity related. But this again, just nomenclature. But yeah, it's another velocity related. But it's something that people usually don't include. Like also the fact of calling them relativistic is just nomenclature in a sense. So if you want to have a look at how this density contrast in Fourier space actually look like with respect to the matter density contrast, it's a biased version of it, where what happens within the parentheses is at first level you have the linear galaxy bias, which depends on the sample of galaxies that you're looking at. Then there's the bit that comes from redshift space distortions. And on large scales, linear redshift space distortions induces a quadruple. So you have the cosine of the angle between the line of sight and your k vector, mu, and this is squared, so this is a quadruple, and this is weighted by the growth rate, so it tells you how much galaxies like flow with the Hubble flow. On top of this, then, if you want to stop at the first dominant term, which is local term, this is Doppler. And Doppler is actually a dipole, so you see this is only depends on mu, not mu squared, and a dipole in real space becomes imaginary contribution in Fourier space. So you have this I on top. Then F is the usual growth rate, and alpha is just the magnitude of the Doppler. And this magnitude of the Doppler is related to the sample that you're looking at. So again, like B depends on the sample. The problem is that these scales have conformal H over K. So it just becomes important with K is very small, so on scales that are very large. And those scales that are very large are plagued by cosmic variance. So people have not included or like it was not important because it's very difficult to measure. It doesn't really contribute on those. If you look at normal scales, like BAO scales, where people usually look for galaxy clustering. Now, the other thing is that this was also pointed out by a paper by Raoul and Daniele Bertacca in 2017. This is imaginary contribution, right? So when you take the power spectrum, so for two tracers T, so for one tracer T, you take the autocorrelation power spectrum, then you have to square this contribution. And these two, real and imaginary, of course, they are orthogonal. And so they just decouple, meaning that the Doppler in the power spectrum scale is H over K squared, so even more feeble in the scales that you measure. And so if you want to make an exercise, this was done by my student Federico and myself, if you want to see to which precision you would be able to measure Doppler with like the most recent galaxy samples, and we did this exercise by looking at DESI, Dark Energy Spectroscoping Instrument, Bright Galaxy Sample, BGS, and Euclid's expected H-alpha emission-like galaxy sample, model 3 is just nomenclature, in different redshift bins. Then you see that if you want to measure this Doppler effect for each bin, well, the precision is not really a precision, right? It's a precision of 100 tens of 100. So there's no point, it looks like there's no way of measuring this. Something that you can do, so if you remember, I told you that this Doppler effect depends on the actual sample that you're looking at. So you thought maybe we can optimize for the sample. So we can look for a subsample of the total one that is better suited to measure this effect. So for instance, the easiest way to do this is you split your sample into a bright subsample and a faint subsample. You can do that, and you see that you gain something. For instance, in some redshift bins, the faint subsample behaves better, or in another redshift bins, the bright one behaves better. But still, the error bar is too large to be able to measure this effect. But if you go back to this expression and you think about this, if you take the cross spectrum between two different subsamples, T and T prime, two different traces, sorry, T and T prime, then the imaginary term doesn't cancel out anymore with the real one. And so you end up with a contribution that is imaginary in the power spectrum, and it scales with one fewer power of H over K, making it less weak, right? And then if you try to look at the cross correlation between the front and the braid subsample, you see that in some cases you can go below the 1 sigma level, and this is just differential. So in principle, if you sum up the total signal to noise of this, you should be able to measure this effect. And the nice thing about this bright faint split is that you can optimize for it. This was a split that was roughly having the same number density of both subsamples, right? But you can optimize, and if you just focus on not on the dash, but on the solid one. This is the delta chi squared that you have on the measurement of the Doppler as a function of the flux at which you split bright from faint. And this curve is actually a maximum, meaning that you can reach you can find the sweet spot for measuring this. Models for the emission lines, for the luminosity function of the H-alpha galaxies from simulations. So these were the things that were put into the flagship simulation for Euclid. These are analytical models that we had to do all the derivatives, etc. Some of these behaving better, some of this is worse. So it depends on the sample again. So model 3 is more degenerate in some sense, yes, probably. And the final, yes. Yeah, sure. Is there a reason because why the model 3 you don't see much difference between the cross correlation? Yeah, it's probably because of the, in the end, it's very difficult to pinpoint a single reason for this, because all this, it depends. So you change something, and then you change the derivative with respect to the response, right, of the number density with respect to magnitude cut or flux cut or the evolution, and also the bias. So it's a kind of a mixture of things. Yep.
Yeah, you can see here alpha T
Yeah.
and alpha T prime and T prime and T are nearly the same, then this factor cancels out and it's equal down, right? So that must be kind of this model 1 and 3, you change the parameters.
Yeah, it's a bit flatter in a sense.
Say that for lower redshifts, that difference is from.
It's a different sample. So for, if you look at this, like for the BGS, this was actually more self-consistent, because for DESI, we had a halo HOD, right, a halo occupation distribution model that accounted for both redshift and luminosity. For one single formula to rule them all, let's say, we were able to compute the bias, the number density, all the biases, right? This was more self-consistent. This relied on some assumptions on the models. We are now doing this with Fede on the measurements of the flagship, so the simulation, trying to measure directly the number counts and so the slope, but still at the beginning, so we haven't resolved that. But the final thing that you can do with this, on top of this optimization, is that, well, now you have the cross-correlation that behaves very well, but why, like, throw out the rest, right? The autocorrelation you still have. So you can construct a multi-trace, what's called a multi-trace data vector, where you take your auto spectra and your cross spectrum and put everything together, taking into account the cross covariance that is like tricky to compute. And if you do so, you do even better. So this is really dependent on how you correctly account for all the cross effects also in the covariance, but this seems to the way to go. And this is what we are actually pursuing and trying to do in Euclid with real data. Yes. Yeah. The reason why BGS, which is actually low redshift, behaves better is because the overall Doppler term scales with as an on top of, as also a scale with 1/r, where r is the distance. And BGS being low redshift, in fact, even if the volume is not that large, you gain from this. Yes. Is the entire, well, this is the HOD that was measured from the 1% data release, extended to the full area. Yes, yes.
But if for test year 1 that you have already, if the signal is that good,
you might already be seeing something. Yeah, there's Jade Piat, you know, the student of Florian Beutler in Edinburgh. She was working on the simulation for this. Jade. Yeah. Yes, Jade. Yeah. So a kind of the sample looks better than ours, unfortunately. They might beat us in time, but yeah. So this is really, it's actually very exciting. The other terms is much more difficult to measure, but this Doppler term seems something that it's within reach now. It wasn't with the previous data sets, but now it is within reach. And this is a nice example of how you can use these cross correlations to beat cosmic variance in particular. The second thing, of course, if you have other questions now or later, no problem. But if I want to move on, the next thing is how you can use, an example of how you can use synergies to beat noise, if you want. So to dig out something of noise that you wouldn't be able to measure. And in this case, I'm focusing on something different, or focusing on the topic of what dark matter is. And you know, there are, the main idea behind dark matter is that it's another fundamental particle. And one of the most studied theory, not the most, but one of the most studied theories in this is weakly interacting massive particles. The idea that particles of dark matter don't only gravitationally, they also have a weak interaction with standard model particles. And the idea is that you have two dark matter particles, then they can just annihilate each other and produce standard model particles. And the standard model particles, the end products at the end of the day will be protons, electrons, so cosmic rays, and photons, right? And so you could try to look for the end products of the annihilations, or even decays, doesn't really matter, the mechanism. But you can try to look for these end products. And in the WIMP paradigm, the mass of a dark matter particle is for the GeV to TeV, meaning that these photons will have gamma ray energies. And this is what people have done. So this is the best ever gamma ray image of the gamma ray sky from the Fermi satellite. What you see here, this bright line in the center is, of course, emission from our own galaxy. And then you see bright spots here and there, rather sparse. These are known resolved gamma ray sources.
So whenever I see these images,
Yeah,
what's the redshift accuracy that you can get from those sources?
nothing. You don't have any information about the redshift. So if the sources are resolved like this, you can then cross-eye identify them. Exactly. But the others are just unidentified. And you see this map is, even if you take out the bright sources, this map is not homogeneous, it's not uniform. And this is due to the fact that, of course, you have a lot of sources that just below threshold, so you cannot detect and resolve them, but they contribute to the what is called the diffuse unresolved gamma ray, not diffuse, to the unresolved gamma ray background, UGRB. And the idea is that if you took out all the known sources and just look at the unresolved gamma ray background, on top of the astrophysical sources, you should also have contribution from dark annihilations or decay or dark matter particles. So what people have tried to do is looking at the gamma ray energy spectrum as a function of energy. And you see here the data points from Fermi. These are all data points, but the idea is the same. The situation, unfortunately, is not much different. Data points are black. And then you see the models from the emission. This is unresolved emission. These are models from the unresolved emission of known gamma ray emitters. Blazars in the first part, mesolened AGNs, star-forming galaxies, and then you have a very low contribution from local pulsars. And of course, these are models for the unresolved emission, so they come with an uncertainty. And this is the reason why you have this large error, like color bands on top. But the main take-home message of this plot is that these data points seem to be well accommodated by a combination of these kind of power laws from these astrophysical sources. Whereas if you had any contribution from a dark matter particle, you would expect to see some special features. You would expect to see a bump somewhere. And the bump would be related to the mass of the dark matter particle, to the channel in which it decays or annihilates, and of course, the magnitude of this bump would be related to the cross-section. So the fact that cross-section or branching ratio, whatever. So the fact that we don't see any spectral feature may mean either that the dark matter doesn't really work this way, or that the astrophysical contribution is just too noisy, there's too much stuff that goes on for us to be able to see. The cross-section is too low, if you want it another way.
I've seen this a few times, but I always have the simple question.
Yeah.
People explain to me and I forget it, but what you see there is the observed energy of those particles, right?
Yes.
So they're coming from all kinds of redshifts.
Yeah.
The buff will be convolved with the...
Yeah. You have to take into account.
Buff, really, cosmologically speaking, it's like...
It's more spread. It's
more spread, but maybe not in 3 orders of magnitude. But
no. You have to take that into account as well.
that is already included in this...
Yeah, this is just a sketch. This is just a cartoon.
Still, it will look pretty much like that.
Yeah, hopefully. Yeah. So something else that you can do. This seems a bit like without hope. So something else that we could do is looking at the anisotropies in these maps. And again, I put just the map for like illustrative purposes, but the idea is that you have the unresolved map. So you take out all the resolved sources. And so you take the spectrum of the gamma ray maps, and you can compute an angular power spectrum, harmonic space power spectrum, like CMB. So you have your CL as a function of the angular multiple. So this is large angular scale, this is small angular scale. This is Fermi data as in 2013, when we started with this exercise with people in Torino, Nicola Fornengo, and others. And this is Fermi data. And in this plot, we put different contributions, like splitting them up, like with annihilating and decaying contributions that were like kind of reasonable, right? For a mass that was reasonable, a cross-section that was reasonable. But you see that basically the Fermi data at the time and today is not much different, can be completely described by a population of very bright, very sparse blazars, that this is L times L plus 1. So if you just look at the CL, this is flat, meaning that they contribute just a Poisson noise. Like this is just Poisson noise from these very bright samples. So the situation here, again, looked not very good. But then the idea that we had back in 2013 was like, well, if dark matter comes from particles that reside in the dark matter structure, you expect to have correlations also with other traces of the dark matter distribution. And in particular, you can try to use a tracer that allows you to filter out all the non-thermal emission, just looking for what correlates better with the dark matter distribution. And galaxy clustering, weak lensing are two things that work very well in this sense. And so what we did was trying to look for direct gravitational probes of dark matter. And in this plot, you see the same models as before, but cross-correlating, in this case, forecast for the cross-correlation of Fermi and Euclid cosmic shear. This is the same color coded before, and the situation is completely reversed. The black line now that wasn't present before is the total signal with error bars, forecast error bars. And blue is an annihilating dark matter model with the same properties as this one. And red is blazars. Now, the fact that the situation is completely swapped is due to the fact that this is unresolved emission. And so, depending on the models, there's a lot of uncertainty in the models, but depending on the models, in general, the idea is that these blazars correlate with the mass of the halo, so that the very bright ones, the one that you see, reside in the very massive halos. Those that you do not see at this energy threshold are probably either far away, distant, or residing in small halos. But if you look at lensing also prefers massive halos, because this is where you have the most massive, the strongest lensing effect. And the annihilation of dark matter particles is much more likely to happen in more massive halos. So in this case, you kind of match the best signal from one part and filter out the other on the other side. So this was the idea at the time. And this idea actually prompted a lot of research in this direction. So people started to look at the cross-correlation, on this cross-correlation, and if they didn't manage to measure it, they could put bounds on dark matter particles coming from these known detections. A group in Japan did many analyses, and ourselves with different cross-correlation with different samples. Gamma ray speaking is always Fermi, but with different levels of, much more advanced data. And this is the kind of standard plot that you see in this analysis, where you have the velocity average cross-section versus the dark matter particle mass. This line is what you would expect to see if the WIMP miracle occurred. And everything which is above these lines is excluded from the data. The plot for NASA et al., so the gamma ray spectrum itself, gave you bounds in 2016 like this, with this analysis with the cross-correlation with the non-detection of the cross-correlation with the kids sample weak lensing survey. We were able to put constraints that were comparable to the original, to the gamma ray only standard way of doing this. And these were forecast for future measurements. This actually happened in 2020. This is something that was proposed for a mission that was never approved. So this is probably not going to happen, unfortunately. But then something more happened in 2020. So this is, we did an analysis using the dark energy survey. You see here the kind of the standard weird shape of the footprint of the dark energy survey, weak lensing survey. And this is the map of the emission, the number photon counts, photon flux from Fermi at the time. So what we cross-correlated were the pink regions that you see here with the map that is behind. And with that, we were able finally to get the first detection of this cross-correlation sigma at the 5 sigma level between this year 1 and 9 years of Fermi. And later on, this year, in January, we managed to do the same with the 3rd year of data detection and 12 years of Fermi at the level of 9 sigma. So now we really have enough signal to noise to start digging out some modeling from this. And for instance, with the latest measurements, we were able to put some constraints on how these astrophysical sources behave. What you see here is the amplitude of the cross-correlation signal, normalized to some units, as a function of the energy. So this is an energy spectrum, if you want. And for instance, what we could say is that the model, so the data actually, prefers a model from the emission of the blazars, which are the most dominant contribution, astrophysical contribution, that is not what you would expect with the power law, but it has a curved spectrum that we model with the log parabola. The meaning of this curved spectrum is probably that there exist 2 different populations of blazars that contribute to the signal, and so you cannot just describe it with one single power law from one astrophysical emitter. And interestingly, the same 9 sigma detection, so the same delta chi-squared between the null hypothesis and what we actually measured, could be reached if you feed the data with a model of dark matter particle with the mass of some well, some 500 GeV, and quite a large cross section, like 20 times the thermal cross section. Of course, we're not claiming that we measure dark matter with these properties, even also because it's kind of in tension what we would expect. But the point is that now there's enough signal to noise that you can actually use this data not just to say I measured the cross correlation, but to do some modeling of the astrophysical sources. This is dark energy survey data, yes. Yeah. Yeah.
Just wanted to understand.
Yeah.
You're comparing the diffuse
Yes.
gamma ray.
Yes, diffuse gamma ray.
Now, there is also bounds from dwarf galaxies
Yeah.
in the dark energy survey, which actually looks similar to the diffuse ones that you showed.
No, that's the interesting thing, right? You get the same sort of the information. It's a very different sort of information. A lot of people look in the gamma ray business, right? They look mostly they look for small dwarf galaxies that what you expect to have to be dark matter dominated. So where you expect to have most of this emission from annihilation or decays of dark matter particles. That is more constraining as a probe, but is very model dependent because you have. Yes, exactly. You have to model the non-linearities of the halo a lot. That calls for a lot of belief in what you have.
This is kind of what I wanted to ask. So when you say diffuse, you are filtering out those, let's say,
Yeah, you take them out of the. Yeah.
individual sources, right? But then, I mean, yeah. So that's the question, right? Why do you think that the signal you're measuring here is different in the sense of having to model the nonlinear part of how dark matter is clumped, right?
Yeah.
There's something there.
There is still a lot of.
Dwarf galaxy measurement, it's in this measurement, right?
Yeah. No, you still have to measure to model the nonlinear power spectrum at least, but it's complementary. So in the end, the fact that they are pointing towards the same scenario is reassuring in a sense that probably our understanding of this is not too far. But definitely after 10 years of playing around with this, what my personal take on it is more than measuring dark matter, this will help us to understand better the unresolved population of these astrophysical sources, which is probably more interesting from this point of view.
Natural question is whether you can combine both things, from the point source
Yeah.
and diffuse, and they have a very good bound in the mass. Because if you go back to, you mentioned that, the dark matter mass is below, 20, 25
Yeah.
GeV. Above 25 GeV are excluded.
Yeah. So in principle, you could. No, it's looking promising, and there's actually a lot of things that you can do. Not enough people to do it as usual, but this is it's getting now with also LSST in the future. Euclid is a bit too deep to do this because the kernels for dark matter annihilation and decay, they peak at redshift 0 basically, right? And so. So if you want to use galaxies, people have looked at this also with galaxies. Now I focus only on lensing, but you can also do with galaxies that, of course, has the uncertainty on the bias. So there's a further uncertainty in this.
That's a very naive question here. So peak for annihilation is actually happening later rather than earlier. That's because of clumpiness?
No, that's just because of you see gamma ray coming from like the nearby more easily than not far away.
In terms of like the history of
No, this happens all the time. Yeah.
yeah, but let's say the luminosity that's being bumped into the universe,
Yeah.
gamma rays or whatever photons in general. So is this like growing with time or decaying with time? If I look back at earlier and earlier times, this is happening more than now.
For annihilation, I say that it's happening more now. Because you want more density, right? Because it scales with rho squared.
Luminosity per commuting volume, it's increasing with time.
Good question. For commuting volume, with the expansion, the accelerated expansions, is what wins between the two effects? I can say at the.
But you need time for dark matter to meet each other.
Yeah. So that's why the more nonlinear the universe is, the more likely this is thing to happen. But then you have the fact that things are getting sparser. So, do I still have some time? Okay, last thing then. How to use examples of how to use cross-correlation to do cosmic variance, examples of how to do cross-correlation to dig signal out of noise, and the last one is how to use cross-correlations to beat systematics. that seem very not super exciting, but actually can lead to actually exciting thing. And in this case, instead of looking at clustering, I'll be talking about the clustering, but from another point of view, the point of view of intensity mapping. And the idea of intensity mapping is just that instead of counting galaxies that you need to resolve, you look at the unresolved emission of all those galaxies coming from the emission lines of some lines that you know. And this is the idea behind intensity mapping in general. And as I was telling before, answering Ricardo's questions, the most advanced way of doing this at the moment is by looking at intensity mapping of neutral hydrogen. And the idea is that neutral hydrogen, so the hydrogen atom has a hyperfine split in its spectrum that is related to whether you have the spin of the proton and the electron aligned or anti-aligned. And of course, the anti-aligned case is slightly lower energy state than not the aligned one. And so even though this is a forbidden transition because it doesn't happen in like standard quantum mechanics, this can still happen because hydrogen is the most abundant element in the universe. And this is the energy of the photon that is released when this state decays into that one. And this energy corresponds to a photon of 21 centimeter wavelength, which corresponds to about 1400 megahertz. Now, the idea is that if you look at the maps of the intensity at these frequencies, you can detect exactly the and you know how this neutral hydrogen populates galaxies that after the end of ionization, this is where it should be, because the rest of the universe is mostly ionized. Then you could see directly the distribution of galaxies that are unresolved. It's a bit like with gamma rays, right? You see the unresolved emission from those galaxies that contribute to that. But you don't throw away any photon. You just count them all. We don't have to detect a galaxy by reaching a threshold of enough signal to noise and then throwing away the others. And the byproduct of this is that you have the redshift for free, because you're literally tuning the radio, right? You're listening to the universe at let's say, 700 megahertz. Well, 700 megahertz is a half of this, meaning that this is at redshift 1. And so you can do this in extremely exquisite redshift precision, because you can channel, the channels of these measurements are very high. The con is the fact that your angular resolution is worse, because you have to average. This is a very feeble effect, so you have to average over relatively large pixels to get enough signal. But people have tried to do it. So the first measurement of this was in cross correlation with galaxies with GBT, the Green Bank telescope, in early 2000. And people have tried to do it for a lot of time, but never managed to do it measuring the neutral hydrogen autospectrum itself, because the signal is completely swamped by foregrounds, right? You have galactic foregrounds mostly, synchrotron emission from our own galaxy, dust, polarized, other polarized foregrounds, etc., that contribute to the signal that you're measuring, and a bit like with the CMB. But with the CMB, the situation between signal and foregrounds is roughly at the same order of magnitude. With intensity mapping, you have something like 3 to 4 orders of magnitude brighter signal that brighter foregrounds that your signal. And well, people have worked a lot on this. The way but you try to disentangle it is by the fact that signals are smooth in frequency, whereas if you look at one single pixel and you pencil beam and pierce it, you're looking at different redshifts, and different redshifts, cosmologically speaking, are uncorrelated. So your cosmological intensity mapping signal is kind of random, if you look at that. So you can try to disentangle that, and people managed to some extent, but there's still a lot of systematic effects that come from the fact that these frequencies are also where satellites, telecommunication, mobile phones, whatever, are contributing. And so there's a lot of, rubbish that comes into your signal, and you have to model out. So this is the reason why people never managed to measure cross-correlation alone. Now, with the Meerkat, which is one of the SKA pathfinders radio telescope, in 2016, Mario Santos, that was my boss when I was in Lisbon, and others, we proposed this large area synoptic survey, MeerClass. So a survey purpose dedicated with Meerkat to measure intensity mapping, with the goal of measuring for the first time to do BAO basically with intensity mapping alone. And this is done in 2 different bands, the L band, which is peaking around redshift 0.5, and the UHF band, which is slightly deeper and covers a range that nicely is covering also what Euclid is doing. So we had the first data, and this is the data that was in this first paper by Jingying Wang in 2021. This is a map of, like, let's say, a few hundred square degree of southern sky for the brightness temperature of map of intensity mapping. That was after has been like calibrated and cleaned, but you still see that there's a lot of residual stuff. You see a big gradient that cannot be cosmological. You see these magenta spots are known bright and known astrophysical sources, and you see that the map is brighter around the sources, so there is some leakage still of signal from those to that. So it's a different business. But in any case, people manage in the Minicourse collaboration to measure the H1 galaxy cross spectrum between this map and maps of different galaxies, in particular using the WiggleS survey, which is a galaxy survey from Australian group. And this is the WiggleS 11-hour field cross-correlated with that data at redshift 0.5, roughly. And this is the power spectrum, the theoretical power spectrum fitting the data, where we left out as a single parameter the total amplitude of the power spectrum. And this total amplitude is basically degenerate between the bias of this H1 distribution in the universe and the total abundance of neutral hydrogen in the universe. And this was fit to this number that was actually in agreement of what we expect roughly with the abundance of neutral hydrogen. Later, with another L-band dataset, so the same redshift but a different patch of the sky, was cross-correlated with the Gamma, another galaxy survey, 23-hour field. Gamma is sparser, is smaller, so the error bars are larger, but roughly we have the same kind of agreement between the two. Now, what I'm going to show you now is the state of the art of what we are doing in trying to measure the autocorrelation spectrum. And this is a work that is carried out mainly by my former master student and now co-supervised PhD student, Matilde Barberi Squarotti, Isabella Carucci, that was in Turin with me, and myself, and all the middle-class collaboration. So that what I'm showing here is a so-called heat map. This shows you in each pixel you have either one of the 64 dishes of Meerkat with a color code that tells you these are the different scans that have been on the sky. And the darker the color, the brighter the color, the more observation you have had with that dish at a given scan, right? It's a kind of depth, if you want. You see a lot of white, and a lot of white is due to this RFI, so it's the radio interference, residual radio interference that comes from telecommunication satellites, etc. And the means by which people look at this is that they look at the time-ordered data, and you see huge spikes of emission, and these are related to either known satellites, or there's a lot of non-known satellites, because they're like military and stuff. And what you do is just you flag the data. You cannot believe the data, so you just throw it away. And you see that we actually had to throw it away a lot of data. It's actually pretty fast. So the nice thing about intensity mapping is that this data is like 10 hours on sky. Okay, so it's 1 night, pretty much. Yeah, cumulative. Yes. So it's really fast. And this map is due to the fact that we keep constant elevations, and so go back and forth, and you have this kind of carpet looking, yeah. And then we had to trim the data, because when you look at the power spectrum, these fringes cause a lot of mode mixing, etc. So better to look at a smaller area, but to take this out. So this is the heat map. And so what we tried to do, once we had cleaned the maps, etc. Good question. It doesn't really matter. No, it doesn't really matter. Yeah. You try to time your observations where you know that there shouldn't be fewer things around, but yeah, you can't really know. So what we did, for instance, was starting by reshuffling this data in order to remove any possible correlations among the scans that happened one after the other. And then we subdivided the data set in different ways. So we subdivided the data set into different scans. At first, we tried it with dishes, but then we saw that actually the way dishes behave is actually well understood. So there's not much crosstalk between dishes. So you can see this is a good one, this is not a good one, and throw it away without. But most of the systematics comes actually from what you have in the sky. And so after reshuffling, we split the data set into 3 subsets that have roughly the same signal to noise. So you see this is larger, but there's more white. This is smaller, but there's less white. Another way that you can do that is by this chessboard division. So you split the data set in 4 quadrants like this. And these 2 only have only have the dish in common. These 2 only have the scan in common. And if you look at the cross ones, they don't have anything in common. They're actually completely independent surveys, if you want, because they look at the same sky, but at different times with different instruments. And so the cross-correlation that we did here were internal cross-correlations by taking everything into account and actually doing internal multi-tracing in the sense of taking the auto cross-correlations, well, the autoless in this case. The big thing is foreground removal. So we proceeded with what's called multi-scale PCA. So you have your map, which is a function, P is the pixel, right? So you have your data set, which is a function of the pixel at a given frequency. And we split this map in a coarse map, which just have the large scales. This is done with starlet decomposition, wavelengths, and things like that. And possibly a set of many higher resolution maps. First of all, Isabella found in a previous paper that given that we have a beam also, right? So we cannot resolve very small scales. Having just a large and a small subdivision is sufficient. We don't need many high-resolution maps. And then we performed PCA on the large and the small maps separately. And this allows to be less stiff, right? So you can resolve, PCA can allow for remove like the synchrotron, which is very important on large scales, in this map, and then it can accommodate for other effects better on small scales. And then you put everything together. The big question is how you choose the number of modes that you can remove from the PCA. And so we started constructing what we call the tablecloths, where you have these maps that in the big rows, the major rows, you have the cleaning, the number of elements of the PCA analysis that you remove from your data related to the cleaning of the large scales here in subset I. The major columns are the number of cleaning that you need on large scales on subset J. And then the block rows and columns, so the small ones, are the same thing, but for the most small scales. And our figure of merit was just, agnostically speaking, was just the reduced chi-squared with respect to a good fit. So everything you see white is a nice fit with chi-square of 1, a reduced chi-square of 1, and blue is overfitting, and red is bad fit. And this we did for a lot of combinations. This, for instance, is for the 3 stripes. So this is the subdivisions into stripes, right? And you have 1 with 2, 1 with 3, 2 with 3. Everything which is gray is just thrown away because it's too, this is just saturated, right? It's not good, it's just right. And then you have like mixture of overfitting and underfitting and some good fits, right? And our approach was to find the combination for each data set that gave the same amount of modes removed in all possible combinations, right? This spot is good here, but it's bad here. Then it's better this combination, I don't know, like this combination 1 that matches what you have on the different side. So this was the overall approach that we had, and then combined everything together. And this is preliminary, but you see the H1 power spectrum, so this is auto spectrum of hydrogen as a function of wave number, measured fit by this kind of multi-tracer, multi-subset analysis. The circles, the bullet points are the combination of the stripes, so 1 with 2, 1 with 3, 2 with 3, and the squares are the combination of the most independent measurements, so the cross. This is my phone, sorry. The cross chessboard, A with D and B with C. Sorry, the other way around. And these are, it's a strange way of looking at it because it is a fit that is done cumulatively. This is one curve that is fitting the cross chessboard, one curve that is fitting the stripes, but the data points are all correlated. It's a single data vector put like in a multi-tracer. It's a multi-tracer without autocorrelations because we don't trust the autospectra. There's too much rubbish that ends into that. It's just a multi-tracer with only cross spectra. And this is the best fit and is in agreement with what we expect. And this is a kind of a 5-ish sigma signal to noise. Yeah, a bit more. And so this is what we are wrapping up at the moment. But at the beginning, we were trying to do this exercise just to see a way to clear off systematics. And then it turned out we stress tested. I mean, we've been working on this for like 2 years. Matilde was doing a master when she started. She's second year PhD now. So we stress tested a lot. We're just keeping stress testing, but we're kind of now convinced that we're measuring something that might be cosmological. And this is a way where you can use these cross correlations, even internal ones, also to get rid of the systematic effects. So to conclude, this is really a great time for cosmological and astrophysical synergies all across the spectrum, even with gravitational waves, which are super interesting. I didn't have time to talk about that, but you're doing a lot of great stuff with that. This cross correlation can be crucial for, at the very basis level, to cross-check the validity of cosmological results. There's so many tensions and stuff going around that if you want to, I mean, the big claim require big, the standard way of saying, right? So just cross-checking across wavelengths is super crucial. But then on top of this, you can use really this to remove or at least alleviate contamination from systematic effects and access signal that otherwise would be buried in noise or cosmic variance. And this is all. Thank you. Thanks. Thanks, Ricardo. Yes. Yeah, autospectral. So there's been a claim, a measurement, a claim in the sense that the paper is still under review by the same meerkat measurements, but this is not meerkat because it's done on interferometric data. So this is visibility, not this, sorry, the other thing. Again, is Mario, Laura Foltz, Zhaoting Chang, and people in Manchester that work on the visibility. So this is interferometric data, but this is very high K. It's like K of 1 to 10, right? It's not really the cosmological signal that usually you want to do cosmology. This would be the first measure. Mm-hmm. No, not much smaller. If you look at it, because you also have into account omega H1. So this measurement falls in agreement with this kind of. It's slightly larger, in fact, than this number, but still within error bar.
How do you see the bias in the power spectrum?
How it enters?
Is
Is the overall amplitude. We just fit for one number, which is the overall amplitude of the signal. Oh, it's not written anywhere. No.
Sorry, I don't quite get it. So, why is it, I mean, when we are just making a galaxy power spectrum, the question about the overall density contribution of that tracer never comes up. In this case, it is intrinsic to the signal that you're measuring.
Yes, because you have the temperature on top. It's a brightness temperature.
It's megaparsec cube microkelvin
Yes.
square.
Yeah. Oh, yeah. If you're looking at like 10 to the 4. Yeah, it's not dimensionless. It's temperature. So the brightness temperature comes with most of the things that are known, but for the total amount, it's directly proportional to the total amount of neutral hydrogen, the abundance. And so basically what people measure, like a B sigma 8 thing for galaxies, in this case is omega times B.
You cancel the delta, but you don't cancel the delta.
Yeah, it's not a density contrast. It's just fluctuations in the temperature.
Some more questions for Stefano? Yes.
So, can you go back at least to the first part of your talk?
Sure. No, there was no primordial non-Gaussianity. Yeah, might have been in the title. Then I decided to trim something out because it was already taking too long.
But my question was toward methodology, right?
Yeah.
So I will assume that these kind of effects look similar as the ones from Simon Kennedy.
Yeah, so there's a degeneracy. Yeah, yeah.
Did you study or do you have comments about the degeneracy?
So there's a paper that we're working on with Federico at the moment. We're looking at how to use this bright faint split also to boost some of the effects of non-Gaussianity. Annoyingly, that doesn't really work. I mean, you can't get too much from that. But what we found actually is that once you add non-Gaussianity, which is h over k squared, and you don't account for these relativistic effects, you do not really bias, not too much at least, is a few % of a sigma, the precision, but the accuracy, sorry, not the accuracy, but the precision changes. So once you do the model properly and you take all the same order of h over k into account, and given that you don't know the magnification bias and evolution bias, so if you want to model these things into your signal, you also have to put some numbers, right, for those, but you don't know them, so you have to marginalize over them. Then actually the error bars on non-Gaussianity enlarge by a factor of a few. Like not massively, but still, yeah. Because, as you say, they are kind of the same. Yeah. Yeah. Mm. Oh yeah, we are modeling also Ricci space distortions. You have them as well. Yeah, yeah, yeah. In fact, yes. So you have a lot of precision. So that measurement that I was showing was in a narrow band between, it's centered around 0.45, but the redshift range is actually is like 5%. It's 0.0, sorry, from 0.4 to 0.45. It's super narrow. In that range, we have 250 channels. So you have 250 maps slices, because the resolution is like kilohertz, right? It's ridiculous. And you have to average some of them, because in some cases, if you're particularly low redshift, some slices will actually slicing up the same galaxy, because it's very near. But once we have, and we modeled the redshift space distortions, the way we modeled redshift space distortion was for matter only, because there's not enough constraining power to tell them apart, to see the quadruple. But yes, then once we we get something more, in principle, you can also have measurements for this. In principle, you can go up to the end of reionization, so up to redshift 5-ish, 4. Ah, down? Yeah, yeah. Thank you. Thanks.
Breaking news of the first measurement
But it's also posted on the, there's a poster by Matilda in